Hi everyone. Just responding to your feedback today on integrated rate laws and half-lives. So first question, what does order of reaction really mean? Does it depend on which reaction occurs first? So at its most basic level, the order of a reaction tells you how the rate of that reaction depends on concentration. At its most basic level, that's all we mean when we say the order of this reaction is first order, meaning it goes as the first power of concentration. And that's why we start with the differential rate laws. Differential rate laws tell you how the rate varies with concentration. So a first order reaction tells you that the rate depends on the concentration raised to the power of 1. That's all we mean when we say a reaction is first order. If a reaction is second order, that just means that the rate depends on the square of the concentration, not just the concentration. Yeah, so at its most basic level, that's all order tells you. There's a reason why it depends on the concentration, and there's a reason why it goes as the square. So we're going to talk more about that when we talk about collision theory in a couple lectures. But at the most basic level, that's all we mean when we say order. If we're describing the order of a reaction, we just mean how does the speed of that reaction depend on concentration. The fundamental reason why some reactions are first order or second order depends on how those reactions occur at the molecular level. Does it depend on a single molecule splitting up? That just only depends on one thing. That tends to mean it's usually going to be a first order reaction. Does it depend on two molecules colliding? That depends on two things interacting with each other. So that's usually a second order process. So there's more to order of reaction. It does tell you something about the molecularly what's going on, how the reaction actually occurs. But at a surface level, from a macroscopic level, from our point of view, that's all reaction order tells you is how the rate of the reaction depends on the concentration of one of the reactants. If you have A, B, and C reactants, do they each have their own orders of reaction? Yes, you can talk about the order of the reaction overall. So I'll give you an example here. I'll make one of them X and the other one B, the other one A. This reaction is third order overall. So I would just say, if I were just talking generally, I would say this is a third order reaction. Because it depends on the first order with respect to X and second order with respect to A. If I add those orders up, I get third order. And your question is, do they each have their own order? Yeah, you can talk about the reaction being second order with respect to A and first order with respect to B. So again, if you're talking just about generally, what does order mean? That's one thing that order means. Order of reaction has other consequences since the rate of the reaction depends on concentration. That depends on how concentration changes. The way that concentration changes is also different for different reactions, and I can talk about that in just a second. Questions about graphs. Is there a quicker way to determine whether something is zero or second order without looking at graphs? What are the indicators for a particular order? To some extent, I guess if I had to answer that, I would say there probably isn't a faster way to identify a reaction as being zero or first or second order other than just by looking at graphs. I mean, it depends on what you have to work with. If I give you the rate law, then you can identify the order immediately just by looking at the exponents. Then you can, that's the quickest way to do it. You don't have the rate law, or better yet, you need to figure out what the rate law is. there's a couple ways you can do it. You can either do it by a method of initial rates, but that requires doing a few experiments and looking at how the rate changes as you change these concentrations. That's one way to do it. And then the last way is to do a graphical interpretation, which is what I talked about today. So is there a quicker way to do it? I would probably argue, if you have nothing else to work with, in a real world scenario, and you don't know what the reaction or rate law is, you just want to do the reaction and figure out the order of it, probably the fastest way to do it is with graphing it out. You do the reaction, you do it once, you measure how the concentration of a reactant, or a product for that matter, how the reactant changes as a function of time, and based on how it varies with time, you can determine its order by doing a graphical interpretation. So let me give you. So in terms of looking at orders and looking at graphs, I figure I would give people a couple other graphs to work with here. So I'll look at one of the graphs I showed today, which was initial concentration versus initial rate. So I plotted up one of them. I said that, okay, a first order reaction has just a straight line. So this is a first order reaction. As I increase the concentration, the rate increases linearly. So if I was going to change this here into a first order reaction, you can see here, okay, if this is my rate, here's my y, here is my slope. The x here is literally your x, that should be times, take that little dot, plus b, and then there's no b here. So if I were going to plot this out, that's what it would look like. So that's if you did a series of measurements where you changed the concentration and you watched how the reactant, the rate changes. If you got just a linear interpretation, you double the concentration, then the rate doubles in a linear fashion, then that means it's going to be first order. That means that it is first order, at least with respect to x. If actually you double the concentration and the rate looks something like this, so it doesn't follow a straight line, it actually follows like a parabolic curve. That implies that it's probably second order or maybe third order, because if I plot it out, if it were second order, this would be my y, this would be my slope, and this would be x squared. Still no b, still no y-intercept. And so yeah, that one's going to have a fundamentally different dependence. It's going to go as the square, so it's going to look like y equals x squared if I plot that out instead. If it were 0th order, so I have x to the 0 here, concentration, anything raised to the 0 is 1. So that means that for a 0th order reaction, the rate is just equal to the rate constant. So it's just a single value. And if I were going to, so this would be first, this would be second. And if I were going to look at how the rate changes with concentration for a 0th order reaction, it would just be a flat line. The rate of the reaction doesn't depend on the initial concentration. It's always the same rate. So in terms of graphical interpretations, those are two ways that you could potentially determine the rate of the order of a reaction. But again, doing that will require you to take a series of data points. So you need to take one there, one there, one there. So you need to do a series of experiments. The other way you can do it is do a single experiment where you measure the concentration versus time. And then again, you can possibly identify the order of the reaction by how the concentration varies with time. Different orders of reactions have different concentration versus time dependencies. A 0th order reaction has just a straight linear dependence of concentration versus time. Those dependencies are given by the integrated rate laws. So again, a 0th order reaction, its rate law goes at the concentration of x is equal to negative kT plus the initial concentration. So there's my y, there's my m, there's my x for the time, the t. So yeah, that one has a a straight line where the slope is negative k. So for this one, yeah, the slope here is negative k. For a first order reaction, if you actually look at how that varies, the expression would be, it goes as the exponential. So you would have some initial concentration times e to the minus negative k times t. So that one is going to look more, so let me get a different color here. This one is going to look more like that. I know in the charts I've shown, I had it going above there. It depends upon the actual value of the rate constant. So if you have a very, very fast rate, this one might be an exponential decay where you have a fast rate. This one might be an exponential decay where you have a slow rate constant. So this would be a low k, this would be a high k. Now I can, clearly this one doesn't look linear, but what I could do is if I take the natural log of this expression, I can turn it into a linear equation. So I can change this to natural log of x equal to natural log of x naught minus kt. That's if I take the natural log of both sides. That will turn this equation into looking linear. So what you will usually do is you will test your data. You'll take your data and try plotting it a couple of different ways. Try plotting the concentration versus time. If you see a straight line, that means it's zeroth order. A zeroth order reaction should have a linear relationship between concentration and time. A first order reaction doesn't. A first order reaction has an exponential decay. Now it might be hard to identify if it's actually following an exponential decay because there's other curves that look exponential but are not mathematically exponential. So what you could instead do is actually take your data and try plotting not the actual concentration, but plot the natural log of the concentration. So you would need to calculate that and then plot that versus time. And if it's going to be if it were first order, that should give you this should give you a straight line for first order. If it's actually second order, if it's actually first order, and you try plotting the, you know what? I should make my colors coincide here. So a first order reaction, if you plot its concentration versus time, you will get a straight line. If the reaction were actually a zeroth order reaction and you try plotting its concentration versus time, you'll get something that has some curvature to it. You'll have something that looks like that, basically. And that wouldn't be a straight line. And again, then that implies that the reaction is not first order. It's either zeroth order or second order. So again, the key idea here is that different orders of reactions have different characteristic concentration versus time dependencies. A second order reaction looks like this: Kt plus 1 over concentration versus 1 over the concentration initial. So yeah, they have different characteristic plots, and so you take your data and see, does it match any of those plots? So yeah, you will get more experience doing this in lab in the next week. So you'll get some experience doing that, and I will certainly be happy to help people do that. Anything else here? I really like the longer PowerPoints today. Could you possibly do more? So yeah, so I got one comment saying that, so I recognize today was a little unusual. I did a little bit more PowerPoint than usual. And I got one comment saying that they liked it, and I got a handful of comments, people saying that it was going too fast. And in my I tend to kind of agree with the majority of people that in general, I don't like doing PowerPoints. I don't think that I think the tendency is to go really, really fast, especially with math. So today was kind of an experiment to see how it goes, and when in doubt, I try to do things on the board, but I knew that I was going to be plotting a lot of things. And to sort of make sure everything was kept in order, I thought it might make more sense to do it in PowerPoint. So some days I will have more PowerPoints. Some days most days I'll try to do most things I can on the board. It gets annoying because I do like to have, occasionally I like to use pictures. And in those cases, PowerPoint can be better for that. So that's my mistake, and I'll try to be a little bit more careful when I'm deciding whether to use a PowerPoint primarily or to use primarily board. Examples with the dots. Can you please explain that again? Sure. So here is this example, and I'll make the numbers. I'm not going to use as many dots here. So I'll leave that up in case I need it. So I'm gonna make this simple. I'm only gonna put in 4 dots. So these are my original 4. And then I ended up with like that. The reaction was supposed to be A going to B, and that took 10 seconds for that to occur. So the first question was, I also told you that this was a first order reaction. So there's a couple of things. The first question was, what's the rate constant? So there's a couple of ways you could do this. You could either use your knowledge of half-lives and notice that, okay, in 10 seconds, the concentration of A decreased by a factor of 1/2. I started with 4, I ended up with 2. It took 10 seconds to do that, so I know that the half-life was equal to 10 seconds. But I also know from the integrated rate law that the half-life of a first-order reaction is equal to the natural log of 2 over K, over the rate constant. So we know the half-life is 10 seconds, so I can determine the rate constant just by rearranging this and solving for K is equal to natural log of 2 over the half-life. Natural log of 2 is 0.693, so then I can just divide 0.693 by the rate constant, by the half-life, which was 10 seconds. So that's one way to do it. The other way, which somebody pointed out in my, I think it was in my 9 a.m. class, is, okay, you can use the rate law itself. So this is one form of the rate law. This is one form of the rate law for the first order reaction. Another form for the rate law is that the natural log of the concentration at some later time is equal to the natural log of the concentration at some, I'll just say, initial time. So what that person said is they didn't think about it explicitly in terms of half-lives. They said, well, I know the initial concentration, or rather, I know the initial concentration might be 4, and I know the later concentration is only 2. I know the time is 10 seconds, so I can just divide that over here. So I can divide by 10, and I also divide by -1. So I end up with natural log of 2 over 4 divided by 10 seconds. And I also need to pull over the negative sign. That should give me the rate constant. If you plug that in, you'll get the same expression here. Or you get the same value here, which was 0.0693. So that was the first part, just like kind of rationalizing, looking at the data and saying, okay, this process, in 10 seconds, the concentration drops by a factor of 1/2. And so just using those 2 data points, initial concentration final concentration and the time that it took to do that, that allows you to figure out the last unknown parameter. Again, that's the whole idea of an integrated rate law. It tells you how concentration is related to time. So you can look at the concentration at two different time points, and then you can relate that to the time it took for it to change from some initial concentration to some final concentration, and that's usually also dependent upon the fundamental rate of the reaction, the rate constant. And the second question here was, what's the concentration after 20 seconds? So after 20 seconds would be another half-life. We said that, okay, in 10 seconds the concentration decreased by a half. The concentration of A decreased by a half. After another 10 seconds, this was supposed to be a concentration after 20 seconds. So 20 seconds total has passed here. The first 10 seconds, concentration decreases by a half. After another 10 seconds, the concentration is going to decrease by a half again. And specifically, I'm talking about the concentration of A. So I had 4, that goes to 2, then 2 goes to 1. So that means I should have now 3 B particles and only 1 A particle. So after 20 seconds, the ratio should be 1 to 3. So in that example, I think it was 4 A particles and 12 B particles left over. How to determine the order of a graph just by looking at it. Frequently, it's not just going to be as simple as just looking at it. But I'll give you an example. So I'll give you an example from what I did today. So the example I did today was I gave you a graph of the natural log of the concentration versus time. So I had a particular process, I measured its concentration versus time, and then I plotted the log of that concentration versus time. And when I did that, I got a straight line. If you get a straight line when you plot log of concentration versus time, that implies that it's first order, because a first order reaction should have a linear dependence on its log of concentration versus time. That is characteristic of a first order reaction. If you plotted log of concentration versus time and you didn't, if you got something that looked, I don't know, like that, then that implies that your reaction isn't a first order reaction. And that's how you basically you can classify it. If it doesn't have a linear dependency on its log of a concentration versus time, then it is not first order. If it does have that characteristic, then it is first order. So how can you determine the order just by looking at it? You can either identify it as being first order or not first order. And that's kind of about as clear as you can get it. So if you look at a curve that goes, if you plot 1 over concentration versus time, and you get, I don't know, if you get a curve that looks like that, then that implies that it is not second order. You can't say, just by looking at this, you can't say if it's 0th order or first order, but you can definitely say that it is not second order. Why? Because a second order reaction should have a linear dependence on the reciprocal of the concentration versus time. That would be characteristic of a reaction that follows second order kinetics. If it followed second order kinetics, it should look something like this. It should have a straight dependency on its reciprocal concentration versus time. So that's generally how you can identify it. It's not so much that you can identify it, but mostly what you'll do is you'll either identify it as being first, second, or zeroth order, or not first, second, or zeroth order. I can't just look at one chart and say that it's zeroth, first, or second. I might be able to say that it is or is not first order, or I might be able to say it is or is not second order, or it is or is not first order, zeroth order. A zeroth order reaction would have a linear dependence if it follows, if I plot up just the concentration versus time. So if I plot up concentration, and I get a straight line, then that means that it is a that means it is a zeroth order reaction. If I don't get a straight line, that means it could be first order, could be second order, could be half order. Those are such things as half orders. We just don't talk about them as much, but they do exist. It could be third order. It's unusual, but it happens. Yeah, it's a way to identify it as being a particular order or not. So you can't, yeah, so that's what I will say. Does the rate law and the rate constant change constantly with second or third order higher orders? No, the rate law is constant. The rate law, again, is characteristic of that order. And so the rate constant, as its name implies, is constant. It doesn't change, and the rate law doesn't change. The rate law tells you how the rate depends on concentration. The rate changes, but the rate law doesn't, if that makes any sense. So again, like I'll give you an example here. I'll work with a first order reaction, which looks something like this. So we define rate here is equal to, if it, let's say it does follow a first order kinetics. So it goes as k to the a to the first power, k times a to the first power. I also define rate as the derivative, the change in a with respect to time. So it's the slope. So the slope here does change. It's always negative, but the slope is changing. At first, it has a very, very fast rate, and over here, it has a very, very slow rate. So its rate changes with time, and its rate changes with order, but the rate law itself doesn't change. The rate law is this guy right here, and that should be constant. And that's going to be true for second order, third order reactions as well. The rate law is constant, and the rate constant is constant. How do we use radiocarbon dating to figure out how old fossils are? Okay, so I'll work through that example again. The thing we assume here is that radioactive events follow first order kinetics, or at least radioactive decay events follow first order kinetics. And that's generally true for radioactive decay. So if it follows radioactive decay, follows first order kinetics, then I know that its rate law is an exponential decay. So its concentration varies as e to the minus kt. So your question is, how can we use radiocarbon dating to figure out how old fossils are? So the idea is, I usually should be able to look at I should be able to take a sample and make an estimate of what its initial carbon content, carbon-14 content was. You know, we assume animals eat things at a particular rate. A certain fraction of the carbon that I'm made up of should be carbon-14. So actually, I'll turn this into carbon here just to keep everything consistent. So we should be able to assume that we know this. So we know the initial amount. We can measure in a fossil so this is how much you started with. we assume we know that. We can measure how much carbon-14 is left in a fossil. The rate constant is known for carbon. I don't have the value memorized. I think it's about 1.4 times 10 to the negative 4 inverse years. So we know the rate constant for it. So this is an algebraic equation with its one equation and only one unknown, which is the time it took for the concentration to drop from this initial value to the amount that's left over. So as long as you can measure how much carbon-14 is left over, you assume how much there should have been to begin with. You know how that carbon-14 characteristically decays, the rate that it characteristically decays, so you can back out how much time would need to pass in order to do that. So after that, it all becomes algebra, or it just becomes a bunch of math to calculate that. But yeah, once you get those values, so what you do here is, okay, I want to solve for, mathematically, what do I want to do? I want to solve for time. So I have an exponential term here. I can get rid of exponentials by taking the natural log of it. So e to the natural log of e to the x, e to some number, is equal to that number. So that's a way I can undo natural logs, or undo exponentials, or get something out of an exponential, is by taking the natural log of it. So what am I going to do here? I'm going to do a couple of steps here. I'm going to move the carbon concentration, the initial concentration, over, and I get this ratio. And I partly did that just so I have an exponential here that I'll take the natural log of, and I'll take the natural log of the other side. Anything I do to one side, I have to do to the other. The other thing to point out is this ratio right here is that percentage I quoted in the problem today. I said that 13% of the carbon was left over, the carbon-14 remained. And that is this ratio. It's the amount that I have left over versus the amount that I started with. That's that ratio. So this is the fraction that remains. I can take the natural log of both sides. Again, if I take the natural log of e to the minus kt, that should be equal to just negative kt. Again, I know what k is, and I'm trying to figure out how much time took for it to get there. So if I continue this down here, I can divide both sides by negative k, so I get negative 1 over k times the natural log of carbon over initial amount of carbon. That tells me the time that it took for this carbon concentration to decrease to that carbon concentration. So again, a bunch of algebra just to get to one thing, and then I can plug in the appropriate values. Again, this percentage here was 13.7%, and then the k value here was given. Okay. Now, in theory, I could do a similar type of calculation with any of these if I knew the initial concentration and the final concentration. I could look at those as well, and I can solve those algebraically. Okay, so what's the difference between the math we were doing today and the math we did on Friday? So the math we were doing on Friday was basically looking at just this one equation. We were looking at, okay, if I change this concentration, how does the rate change? And we were doing an analysis of method of initial rates to notice that, okay, some reactions go as the square of the concentration, meaning their rate goes as the square of the concentration. Some of them are 0th order. Some of them don't depend on the concentration at all. So the math we were doing that day was basically looking at this equation. How does the rate depend on concentration? The math we were doing today was working with all of these equations. We're just looking at not how does the rate depend on concentration, but how does the concentration depend on time. So time is a derivative with respect to time. Rate is a derivative with respect to time. So these equations are related, but they're related through a little bit of integral calculus. So yeah, we are doing slightly different math, but it is similar. But essentially, yeah, we're looking at the fundamental differential equation. We're looking at the differential equation from two different perspectives. Either working just with that differential equation, looking at how the derivative changes with concentration, or just looking over here is how the concentration changes with time. So we're looking at two different sets of equations. How does a neutron turn into a proton? A really detailed analysis of that, I have to plead ignorance. Because to really discuss that in any accurate detail requires a discussion of particle physics, which I admit I don't know that much about particle physics. But basically, neutrons and protons aren't individual. They aren't. They're what we call composite particles. Composite, whatever. They themselves are made up of other components. They're made up of three other subnuclear particles called quarks. So you can rearrange those quarks, and as a result, you can change a neutron into a proton by changing the identity of those quarks. So that's essentially what goes on in what we call a beta decay process, where one of the neutrons switches its quarks and it turns into a proton. That process causes the creation of an electron, because when you change the neutron into a proton, you're creating a positive charge. The universe does require conservation of charge, so that means that, okay, if you create a positive charge, you also need to create a negative charge to make sure that you aren't creating charges out of nowhere. I mean, you are allowed to create particles. Theory of relativity asserts that you can make a relationship between mass and energy. So you can borrow a system can borrow energy from the universe to change matter from one form into another, to create matter by taking energy from someplace else, or converting matter into energy, and vice versa. So you are allowed to change particles in that regard. I hope that answered your question. I really feel like it didn't. I gotta look into that. Okay. I think that's most of the feedback for today. If you have further questions, please come by and stop by my office. I'll be here for most of the day tomorrow. I'll be here until probably around 5 or 6-ish today, and usually, again, yeah, I'm in my office at any given hour. So please stop by if you have questions, and if not, I'll see everybody on Wednesday. Oh, was there anything else? No, I think that was it. All right, I will see everybody on Wednesday.